Hello everyone, my name is David Felipe Sorro Pulido, and in this video I will gonna explain my final project for Analog Electronic 2. And the project consists of an audio amplifier, or more generally, an analog signal amplifier, designed using a discrete MOSFET transistor. In this presentation I will explain how it works by analyzing each stage of the circuit and explain step by step. Okay, let's go. The heart of this project is the MOSFET transistors. More specifically, I used the ALD1107I and LAD1107 integrator circuits. Each package contains 4 matched MOSFET transistors. The ALD1106 includes 4 N-channel MOSFETs, while the ALD1107 includes 4 P-channel MOSFETs. Step by step. Now let's see how the amplifier works by analyzing each stage of the circuits. Step 1. Current mirror. The first stage of the amplifier is the current mirror, designed to provide an output current of approximately 16 microamperes. Before designing the MOSFET transistors were experimentally characterized to obtain their electrical parameters, as shown in the picture. Throughout the project, the in black and P black ALD1106 and ALD1107 device were used. Since each integrated circuit contains 4 matches of MOSFETs, each transistor was individually identified as shown in the picture, like ALD N negro 1, N negro 2, N negro 3, and N negro 4. Using the measured parameters, the current mirror was designed. The calculated current gain was approximately 0.97, required a reference current of about 61.8 microamperes to obtain an output current close to 16 microamperes, which at 2.5 volts power supply. The calculated reference resistor was 65.7 kilohms. So the closest standard value of 68 kilohms was selected. The measure of the current was 69.7 microamperes, resulting in an experimentally mirrored current of approximately 67.9 microamperes, which is very closest to the design target. The final experimental implementation of the current mirror is shown in the picture. The step 2 is a common source amplifier. The second stage of the project is a common source amplifier, which provides most of the voltage gain of the circuit. The experimental setup is shown in the picture. Through the amplifier, the value of RB1 and RB2 to the drain resistor were calculated during the design. The early effect was considered to obtain more accurate operating point for transistor M black 3. The effective threshold voltage changed from 0.467 to approximately 0.772 volts. The drain resistor was selected to ensure that both the current mirror and the amplifier transistor operate in saturation region, providing a linear amplification. Finally, the voltage gain was measured experimentally with an input signal of 26 millivolts peak to peak. The output reached approximately 182 millivolts peak to peak, resulting in a measurement voltage gain about 7 volts, which agrees well with the theoretical calculations. Step 3. Differential pair and active load. The third stage of the amplifier is the differential pair, which amplifies the difference between two input signals while rejecting common mode noise. To increase the bias current, the mirror reference resistance was reduced from 68 kiloohms to 34 kiloohms by connecting two 60 resistors in parallel. A trimmer potentiometer was also added for compensate for transistor mismatch, allowing both branches to reach nearly identical drain currents for approximately 58.7 microamperes. The experimental setup and measurement results are shown below in the picture. With a 14 millivolts peak difference input, the amplifier produce a 1488 millivolts peak to peak differential output, corresponding to a different voltage gain to approximately 12.2 volts. The measured CMRR was 36.6 dBs, demonstrating good rejection of a common node signals. The output resistance of the stage was also measured experimentally with a trimmer. To improve the amplifier performance, the drain resistors were replaced with MOSFET active loads, as shown below. Unlike passive resistors, active loads provide a much higher equivalence resistance, increasing the voltage gain without requiring later resistor value or higher supply voltage. The experimental implementation and oscilloscope results are in the pictures. Step 4 is the power stage. The final stage of the amplifier is the power stage, whose purpose to provide sufficient current to drive the load while preserving the voltage obtained in the previous stage. Following the design procedures, the required bias voltage was approximately 3 volts. The final components values were selected: RB1 equal 3.8 kilo ohms and R1 equal H2 equal 4 kilo ohms. Since 4 kilo ohms is not a standard resistor value, trimmer potentiometers were adjusted experimentally to obtain this resistance. During the first implementation, the circuit did not operate correctly because of an assembly error, and one BD140 transistor was damaged. After change dates, the stage is worked as expected. The final experimental implementation shows in the picture. Step 5 is the feedback stage. The last stage of the amplifier is the feedback stage network. Its purpose is to feed a small portion of the output signal VO or VO output back to the operation amplifier. This makes the amplifier more stable, reduces distortion, and sets an overall voltage gain. In the design, Vx is the signal coming from the differential amplifier, Vg is the output of the TL071C that drives the power stage, and VO is the final output connected to the loudspeaker. Following the laboratory width, the feedback resistor RB was calculated to be approximately 3 kilo ohms. Instead of using a fixed resistor for RA, a potentiometer was used. This allows the feedback radio to be adjusted, changing the amplifier gain to acting as a simple volume audio. All the stages explained previously can be submerged in the following three main blocks: differential amplifier stage, feedback stage, and the power stage. The following video shows the final operation of the amplifier. And the conclusion is that this project allowed me to apply many of the analog electronics concepts studied throughout the course, including current mirrors, common source amplifier, different pairs, active loads, power amplifiers, and negative feedback. Finally, I would like to thank the Professor Maribel Anaya for teaching the lecture sessions and the Professor Carlos Furnieles for doing the laboratory sessions. Thank you very much for watching.